In this video, we will see some questions on small signal analysis to find the output resistance. Initially, they have asked me this circuit first, and they went to this one, and then finally this one. See, they are asking the output resistance set for each circuit. We know that for small signal, for a MOSFET, the small signal equivalent is this gate terminal, and from drain to source we have a current of GMVGS and the resistor of R0 between drain and source. This is drain terminal, this is source terminal. So this is because of the channel length modulation, and they have told that the channel length modulation exists. We have to consider R0. The first circuit is this. Copy. So we'll replace each MOSFET with its small signal equivalent. So for the top one, let us say this is M2 and this is M1, and it is GM2 VGS2, and output resistance is R02, and for M1 it is GM1 VGS1 and resistance of R01 from drain to source. The gate of M1 is connected to ground, and also the gate of M2 is connected to ground. Let us say I am applying a test voltage of VT and an IT current is flowing here. If we see the VGS of MOSFET 1, VGS1 is 0, because the gate is connected to ground, the source is also connected to ground. The potential difference between those two is also 0. So this goes to 0. So I can simply remove this. So nothing is there. It is like a resistor R01. Now to find the output resistance, R out is given by VT by IT. I have to find the relation between VT and IT. So by KCL, let us say this is some current and this is also some current. The sum of these two currents, the entering current here is IT. This is equal to these two currents. If we apply KCL here, the sum of these two currents has to be IT here. So the current flowing here is IT. Okay, so the voltage at this node is the current flowing in this resistor R01 into the current flowing in this resistor R01 into resistance. So this node potential is IT times R01. So if we see here, the source of M2 is connected to the drain of M1. So the drain potential is IT times R01. VGS2 is VG2 minus VS2. Here VG2 is 0 volts and VS2 is minus IT times R01. So VGS2 is minus IT times R01. So the current flowing in the above direction is from source to drain is Gm to IT times RO1. So by KCL, these two currents are entering the node. Let us say the current is leaving here. So the current flowing in this resistor RO2 in this direction. So the leaving current in this node is sum of these two currents by KCL. So I will take IT common, so it will be 1 plus Gm2 RO1. So now we have to find out the relation between Vt and It. So we have to find Vt in terms of It. So Vt is the voltage drop across this resistor plus voltage drop across this resistor. So Vt is the current flowing in this RO2 is It times RO2 into It times 1 plus Gm2 RO1 plus current flowing in this resistor is It and the voltage drop is It times RO1. Vt, if I take It common, this is RO2 plus Gm2 RO1 RO2 plus RO1. So Vt by It, that is RO1 is RO1 plus RO2 plus Gm2 RO1 RO2. There is a standard result that we know. This is by KCL and KVL. Simple KCL and KVL, we can obtain this result. But now we will see the intuition behind it, how we got this result without any KCL or KVL. This is RO1, this is RO2, this is M2 transistor. Let us say this node potential is Vt and the current flowing is It. What I will do is, I won't apply any KCL or KVL. I'll just find out the node voltages and branch currents in each resistor and MOSFET. So we know that the current flowing here is It. This node potential is It times RO1. So what is happening here is, the gate node potential of M2 is tied to ground and you have source potential as It times RO1. So the current flowing in the above direction is Gm times RO1 times It. So you are supplying a current of, you are giving a current It and Gm2 times RO1 times It current is flowing in the above direction. So effectively the current flowing in this resistor is It times 1 plus Gm2 times RO1. So Vt is RO2 times the current flowing. Let us say I have a resistor initially let us say I have a simple configuration like this. And I have to find the output resistance R out. In this case VGS will be 0 and I will be left with only RO1 if it is M1. So if voltage is VT and current flowing is IT, VT is nothing but IT times R1. If IT current is flowing through R1 resistor, the equivalent R out is R1. But here it feels like IT current is flowing through 1 plus GM2 times RO1 times RO2 resistor. So the resistance we are finding this current, right? VT is IT times 1 plus GM2 RO1 times RO2 plus IT times RO1. So if IT current is flowing through R1 resistor, the equivalent resistance is R1 here due to this resistor R1, and here it is like a resistance of RO2 times 1 plus GM2 R1, which is nothing but RO2 plus GM2 RO1 RO2 plus R1. This is the total overall output resistance. Here we are giving a current IT from the source. This is the source, VT is the source, and IT current is flowing here. But this IT current is flowing through this resistor RO1 and it is developing a potential of IT times RO1, and this is causing a current of GM2, this node potential times GM of this transistor. What is transistor essentially doing? The drain current of transistor is GM times of VGS. So here the gate VGS potential is IT times RO1 minus IT times RO1. So the current flowing from source to drain is GM times of this potential, GM times of IT times RO2 current is flowing up. So these two currents are added and flowing in this resistor RO2. So effectively this resistor looks like a resistance of 1 plus GM2 R1 times RO2, because initially the current flowing in this RO1 resistor is IT only, but here a current of IT times 1 plus GM2 R1 is flowing. So the effective resistance provided with this becomes 1 plus GM2 RO1 times RO2. So this is the intuition I got from this. So while going to the second question, this now becomes easy since we solved this. Now we know the format. The output resistance is, let's say this is M2 and again this is M1, GM2 RO2 RO1 plus RO2 plus RO1. But we know that for this configuration, for diode connected configuration, the output resistance is R equivalent is 1 by GM parallel RO1. So if GM R0 is far greater than 1, we can say that R equivalent is approximately 1 by GM. So R out becomes GM2 times RO2 times 1 by GM1 plus RO2 plus 1 by GM1. They have said that both the GMs are equal in the interview. So RO2 is both GMs will get cancelled. So RO2 plus RO2 plus 1 by GM1. This is just putting these values into the common equation output resistance format, but we'll just go again and see what is happening another time, similar to the above case, how this resistance got increased. So the resistance here is 1 by GM1 and we have a resistor RO2 here, and node potential of VT, applying a test voltage VT and the current of IT is flowing. So the current flowing here is IT. This will develop a voltage of IT times 1 by GM1, IT times 1 by GM. Let us say both GMs are equal, IT times GM. So GM times this node potential, current will flow in this direction. So GM times IT times 1 by GM current will flow. So the current flowing is IT from source to drain. So the current flowing here is 2 times IT. So VT is IT times 2IT times RO2 plus 1 by GM times IT. So RO2 is 2RO2 plus 1 by GM. This is the same result we got up, but here we know that what is happening. A current of IT is flowing from the test voltage, and this current is flowing to this resistor 1 by GM, and it is developing a potential of IT times 1 by GM at the source. This results in a current IT from source to drain. These two currents will combine and will flow through RO2 resistor. 2IT current will flow through RO2 resistor. This will make this resistor look like a resistance of 2RO2, and IT current is flowing here, so 1 by GM resistor for this resistor. So 2RO2 plus 1 by GM is the answer for the second part. And third part is an interesting one. So earlier what we did, because it is diode connected, we know that the equivalent resistance is 1 by GM parallel R1, but here it is not the case. Here they have given a gain of 1000 from drain to gate. This node potential is VT, so 1000 times VT voltage will come here, and a current of 1000 VT times GM will flow through from drain to source under resistance of RO1. IT is sum of these two currents, the current flowing from MOSFET drain to source and the current flowing in RO1. IT is 1000 VT times GM plus VT by RO1. If we take VT common, like 1000 GM plus 1 by RO1. If we do VT by IT, we will get R equivalent, that will be 1 by 1000 GM in parallel with R1. Earlier we took 1 by GM parallel R1 as 1 by GM. Here the resistance is even smaller, so this will be 1 by 1000 GM. So now this will look like this. Thousand GM and RO2. Now this is VT and the current flowing is IT. So this node potential now is 1000 IT by 1000 GM, this node potential. So now current flowing is IT by 1000. The current flowing here in RO2 is IT plus IT by 1000, that is IT times 1001 by 1000, which is approximately IT. So now RO2 will be, here the current flowing is IT and here also the current flowing is approximately IT. So it will be IT times, if I write VT is IT times RO2 plus IT times 1 by 1000 GM. This is 1 by 1000 GM. 1 by 1000 GM. So RO3 is RO2 plus 1 by 1000 GM. Because the current flowing from source to drain in this case has decreased by a factor of 1000, it is like very small. So the current flowing in RO2 resistor now is IT. Unlike the other case, the current was 2 IT and it was some 1 plus GM 2 RO times of IT. But in this case, the current flowing in RO2 is approximately IT, so the resistance will be RO2 plus this resistance 1 by 1000 GM. Thank you.